In this lesson, we'll learn how to hypothesis test the difference between two means. This is question 2 in this series, and the difference between this question and in question number 1 is that in question number 1, the variances were the same. This time the variances are different, and I'll teach you how to approach this sort of problem. The question reads, an experiment was conducted involving the comparison of the mean heart rates following 30 minutes of aerobic exercises in females aged 20 to 24 as compared to females aged 25 to 30. For this experiment, 10-second heart rates are recorded on each participant following 30 minutes of intense aerobic exercise and converted to beats per minute. The sample data is found below. Take a look at the sample data. This column is for 20 to 24. This column's for 25 to 30. The sample sizes are below 30, so we'll be using the t-test as opposed to the z-test. This is the means for both groups and the variances. Use the data to test if there is a significant difference in the mean heart rates following 30 minutes of aerobic exercise between the two groups. So we'll start with the null hypothesis. The null hypothesis will be this group, which I'll call 1, and this group are the same. And the alternative hypothesis is the opposite of this, where it's mu sub 1 does not equal to mu sub 2. Now, just as we did in question number 1, we will calculate the t observed, but the formula for when the variances are different, the formula for t observed is different. In addition, the degrees of freedom formula also changes. So make sure you make a note of that, and you make sure you read the question carefully for the variance part. Okay, so concentrating here, the interesting part about this numerator is that mu sub 1 minus mu sub 2, we don't have that information. But if we rearrange this and bring that over, we have mu sub 1 minus mu sub 2 is equal to 0. So this part right here becomes 0. That's good. Remember the difference between x bar and mu. Mu is the average of the entire population, whereas x bar is the average of the sample. We have that. We don't have the standard deviation. We've been given the variance, but from the variance we can obtain the standard deviation, and that's this part here and that part there. Actually, come to think of it, if you look carefully, the variance is technically the standard deviation of the sample squared. So all we have to do is substitute that value right into there, and we can ignore this power of 2. Calculating this, we have 15 minus 10, that's these two, minus 0, over, at the bottom, the square root of 40 over 15 plus 10 over 10, right? 10 and 10. That will be our t observed. Oh, and by the way, I didn't mention this. I did mention in question number 1. If your hypothesis is equals and not equals to, use two-tailed test. So just keep that in mind for later. All right, at the top we have 5 over, and you know what? Let's just use our calculator. 15 minus 10, that's 5 divided by the square root of 40 over 15 plus 10 over 10 is 1. Altogether, we get 2.61. 2.61. 2 decimal places is good enough. Now we have to calculate the degrees of freedom. We are using the t-test after all. And this part right here, SE, stands for standard error. Standard error is the same thing as S over the square root of n. So we need to find S, and the relationship is that variance is equal to S squared. Therefore, 40 is equal to S squared. We square root these numbers and place them everywhere we see an S. As you can kind of tell, it's going to be a little mess figuring df. So let me just dedicate some room here. Now, rather than wasting the rest of your time putting this all into our calculator, I'm assuming you already know how to do that. You should end up with a df equal to 21.7, which is 21. You always want to round down for the degrees of freedom. Using what we found earlier of 2.61 and 21.7, you now have everything you need to find out T critical in your T chart. Here's the T chart. This is the degrees of freedom of 21. They don't tell us the significance level in the question, but if they don't, just use 0.05. It's two-tailed. We're right here. If we scroll all the way down, we get 2.080. The T distribution chart will look like this, given what we just found. So T critical is 2.08. We have this part as our rejection region, negative 2.08, and this part as 2.08, and in the middle it's 0. What we found earlier was 2.61. 2.61 actually exceeds 2.08, should be over here. It falls in the rejection region, so we have to reject the null hypothesis for this one. So I'll write down reject null hypothesis in favor of the alternative. The means are not the same between the two groups. Obviously, the age difference creates a difference in the data collected, and so we can say that there's sufficient evidence at 0.05 significance level to conclude a significant difference in the mean heart rates between the two groups. That's the answer to question number 2. Make sure you watch question 3 for another example that's a little more involved, and we hope to see you soon.